classical world, we represent information in terms of the classical state of an object. In analog form, we could represent a number as, for example, the length of some rod in meters, or the value of an electrical potential in volts. In digital form, we represent numbers usually as a sequence of bits that are either 1 or 0. We can represent the 1 or 0 physically as, for example, an object being up or down, or a device being on, that is passing current, or off, that is not passing current, or as a voltage being high or low. We can use similar methods in quantum mechanics too, but in quantum mechanics we can also use superpositions in representing information, such as a superposition of up and down. In a classical world, for one physical system, equivalently, a system that was half up and half down could be represented by it being horizontal. That kind of classical superposition does not have quite the richness of quantum mechanical superpositions. Remember, with spin, for example, that right and left can be represented as superpositions of up and down. We can also represent forward and backward as superpositions of up and down. But in quantum mechanics, we can go even beyond this. We can have superpositions of multiple systems, so-called entangled states, that have no classical analog. And measurement on a quantum mechanical system in a superposition can have quite a different result from that in a classical system. Specifically, in quantum mechanics, we have the process of collapse into an eigenstate. The concept of entanglement and the process of collapse under measurement give different opportunities in handling and processing information in quantum mechanics. These opportunities lead to the field of quantum information. This field includes areas with intriguing names like quantum cryptography, quantum computing, and even quantum teleportation.